Okay. So good afternoon, everyone. So today I'm going to speak about physics-informed neural network on continuous variable quantum computers. And actually, this is a great sequel to the talk before, because I'm actually going to answer to give an idea about what we would like to do with quantum neural network on continuous variable quantum computers. So the organizer made a good job there. To start, I would just like to tell you where I'm from. I'm from the Quantum Intelligence Lab in Milan, under the supervisor Enrico Prati, and there are also 3 other PhD students here, so if you would like to attend any of their speech, these are their sessions. So, let's start. The goal of my project was to solve differential equations using the continuous variable quantum computer. So we built a physics-informed neural network on the quantum neural network architecture that we could build on the continuous variable quantum computer. The outcome, in the end, was an enhanced accuracy and efficiency of existing methods and broaden their applicability to new differential equations. So, to give the context of what we're talking about, we want to solve partial differential equations. Amongst the numerical methods we can use, there are physics-informed neural networks, which embed the physical laws into neural networks. In particular, we want to build this kind of networks into the quantum computing architecture. So this is the scheme. On the left-hand side, we have neural networks and their physics-informed methods to solve differential equations, and on the right, we have continuous variable quantum computers. So, briefly, to introduce you all about physics-informed neural network, we have a neural network, a parameterized neural network, in this case a feed-forward neural network, which has as the input the variable of our implicit function we want to find into the differential equation, and the output would be the actual implicit function. We differentiate the neural network using the chain rule, and we're able to obtain partial derivatives, which then are plugged into our loss function, which is the differential equation put into this form. Also, we can embed any other physical laws, and especially boundary condition and any other term which might help the convergence of the neural network towards the desired solution. So what we actually do on the continuous variable quantum computer, we encode the variables using a displacement gate. We use a parametric continuous variable quantum computer, and in the end we measure. The parameters, of course, are in the quantum gates specifically, and I will show you now how we build it exactly. So on the input data, we have the states which are encoded using displacement gates, and there are however many Q-modes channels we want, and we want to have a feed-forward neural network and something mimicking this feed-forward neural network using the continuous variable quantum computer. So we have the input state and the side transformation, and we will use the quantum neural network to obtain it. Specifically, to have the elements of the feed-forward quantum neural network, first, with the matrix multiplication, we can use interferometers and squeezing gates by using this decomposition where U and V are singular matrices. And then we can add a bias term through the displacement gate, and then the activation function using any non-Gaussian gate. Specifically, we simulate using the Kerr gate. So this is the whole neural network, quantum neural network layer, in which the first 3 parts are the W multiplication, then we have the displacement gates for the bias term, and then any non-Gaussian gate for the activation function. So this is the whole structure of the network we will be using for the experiments and the simulation. So to collect everything together, we have the encoding in the beginning of the variable of the equation we want to find and the implicit function. Then we have the layers of the quantum neural networks, which are parameterized, and in the end we measure the expectation value of the quadrature of the output state. This expectation value will be the output of the quantum neural network and the solution of the implicit function and the solution of the differential equation. After we have the solution, the output of the implicit function, we can train the neural network using the loss function, as said before, and we can optimize the weights of the neural network back again and do this over epochs to make the quantum neural network obtain the desired solution. In particular, for the experiment for the simulation I will show, I use TensorFlow and Strawberry Fields by Xanadu, and it was all simulated on a classical hardware. So let's get on with the first result. We analyzed a 1D Poisson equation with this boundary condition and this domain, and in particular we used this quantum neural network structure. So as you can see, the values, the input were encoded through displacement gate, then this 2Q mod layer of the neural network was used, and then it was measured. Particularly in this instance, we, to improve the state of the art of the current solution in this field, we used the second output to estimate the derivative of the first output. This was crucial to sidestep problems of the nested derivation of the neural network. So we, since we are talking about a variational quantum algorithm, we can plug anything we want into the loss function, as I said before, and this will help us through the convergence. So in this specific case, we put in the loss function that the derivative of the first output of the neural network would be the second output. Therefore, the second output would approximate this derivative. These are the results. We can see the approximation in orange, and the dotted line, the analytical solution of the equation, and we can see that over many epochs, the solution converges to a great precision. Let's get on the more complicated equation. In this case, we wanted to solve the heat equation, and the heat equation was actually solved in a 1D environment, so was the time evolution of this initial temperature distribution, and a similar network was used. The only difference was that in the second encoding lane was used the time, so since it's a two-variable differential equation, and also in this case, the derivative of the first output is approximated by the second output. So these are the results. As you can see, on the time domain, the heat, the initial Gaussian distribution propagates over time, and we obtain a loss function in the order of 10 to the minus 3 after 1,000 epochs. So this is kind of the summary of the results we have. We had this new architecture, and we use it to solve these two equations and showcasing the capabilities of this differential equation, of this quantum physics informed neural network to solve partial differential equations. Key takeaways I would like you to have from this talk is that this quantum physics informed neural network on the simulation side is actually able to solve partial differential equation, and it could potentially give higher expressivity compared to classical physics-informed neural network. This is a field we would like to discover more. We have some preliminary results, and but it's much harder to prove something like that for just the quantum case. But we have some leads on that. And one of the most interesting part is that instead of using classical data, we could use quantum native data to input into our neural network and process directly that. If you would like to check more the discussion and methods used, we have a paper on that on the archive. And that's all. Thank you very much.
Hi, thanks for the talk. So I have a question about, so I'm curious why you want to encode the information in a continuous variable and utilize quantum convolutional neural network to solve the differential equations. I mean, I'm curious about the advantage not using convolutional neural network with traditional physical info neural network.
You mean like what? Just in general, why using the quantum neural network instead of the? It's just an experiment. As I said, it could lead to different possibilities. In this case, it was just to prove that we are able to do it. For now, of course, it's much worse than a classical neural network because firstly, we are simulating it, and it's not comparable. But for example, we try to use the same number of parameters for the classical network and the quantum one, and we would see that we are able to achieve a higher precision with the same number of parameters. So maybe at one point it will be better, but we're on the we have to keep a bit trying to see where we're going.
Okay, thank you.